A very good morning to all. Welcome back to this course of micro engineering. So, from the previous lecture, we have completed successfully the different types of microwave transistors and the some type of specialized diodes we saw in the last lecture. So, today we will continue further with the other two remaining types of special diode. So, in today's lecture, we are going to see construction, working, principle of operation, uses of the remaining two types of special diode, that is tunnel diode and varactor diodes. The varactor diode application wise we are going to see in detail with a different application, a separate lecture we will devote for the application of a varactor diode, that is in the case of parametric amplifiers. So in today's lecture in semiconductors, we will continue exploring the feature, construction, operation and applications of tunnel diode and varactor diodes. So first of all, we will start with tunnel diodes. So tunnel diodes are specially used semiconductor microwave devices. They are used for a variety of different applications, such as they are used in typically the amplification of the microwave signal, as well as they are also used as a source of microwave frequency. So tunnel diodes are sometimes also known as a Isaki diodes. Okay, the name Isaki stands for the name of the scientist, Japanese scientist, who originally found out the operation of tunneling mechanism, which we normally call it as a quantum effect, in the special type of a semiconductor diode, which will provide us a negative resistance effect. Right? So tunnel diodes are sometimes also called as a Isaki diodes, right? And these diodes, they do have a very important property that at certain applied voltage, these diodes are going to provide us a negative resistance. Now, what do we mean by negative resistance? A negative resistance phenomena is the process in which when the applied forward bias voltage across a diode is increased up to certain limit, and when it crosses a certain threshold, the current increase instead of increasing, the current will start decreasing. So normally we know that whenever we apply the voltage, the current will start flowing through the particular devices, and if we increase the magnitude of the applied voltage, the current also linearly tend to increase, right? So this is a normal behavior. So let us say I have one diode over here, a semiconductor PN junction diode, right? So when I forward bias this particular diode by a DC voltage in this way, okay, so we will get a forward characteristic curve. With the applied voltage, we will get a current, so in this way. So what happens over here is, especially when this particular normal PN junction diode is consisting of silicon or germanium, especially when it is a silicon, then the cutoff voltage or the threshold voltage when the applied DC voltage crosses around 0.7 volt, the current will start increasing. And with the increase in voltage, the current will also increase. So this is a linear behavior. Now, there are certain diodes in which when we exceed a certain threshold applied voltage and when we extend the voltage beyond that, instead of increase in current, what we will get is we will start getting decrease in the current. Even if we increase the applied voltage across the diode, after a certain voltage, the current will start decreasing. So that means this is a negative resistance behavior. So if we take the ratio of voltage to current in this particular case, now here the applied voltage is V and the current is I. Okay, so if I take the ratio V divided by I will get a resistance, right? So the applied voltage is increasing. Okay, so instead of increasing the current with increase in applied voltage, the current start decreasing. Okay, so theoretically when you substitute the values of voltage and current, you will get a negative resistance, right? And this negative resistance is a very unique property which is exhibited by certain types of diodes. Okay, and this negative property of these particular diodes are getting utilized in the applications such as amplification, oscillation, right? So in order to possess this particular property of a negative behavior, the diodes or the devices must be constructed with certain different types of a material. So here whatever we are going to discuss the tunnel diode, this tunnel diode is going to possess this particular property of negative resistivity. Okay, so this is a property of negative resistivity. I write here. So just in a simple term, I explain you what do we mean by negative resistance. And later on we will say that when any particular diode is supposed to possess negative resistance, it can be conveniently used to amplify the signal as well as to produce the microwave signal. Okay, so for time being, you just remember that any particular device or diode, if it possesses a negative resistance property, then that particular diode or device can be used for amplification of the microwaves as well as it can be used for generating the microwave itself. So let us see the construction and the working principle of tunnel diodes. Now the tunnel diodes are characterized with quantum tunneling effect. Now this term is very important. So what do we mean by quantum? The quantum tunneling effect is the tunneling effect. Now the literally meaning of a tunneling effect is digging mechanism. Okay, so the tunneling means digging mechanism. Right, I will write over here for understanding. By means of charge carriers. So the charge carriers are literally going to dig. They are going to dig the junction width, the barrier potential which the diode is supposed to offer. So any diode, we know that it is going to provide a certain barrier, junction barrier, right? So this junction barrier width is penetrated by the charge carrier, and the penetration of the junction width or the barrier potential by the charge carrier of the diode, we call this mechanism as a digging mechanism. Okay, and this digging mechanism is been given a different name called as a tunneling effect. Now why it is called as a quantum tunneling effect? Because here the digging operation or the penetration operation of the barrier potential provided by the diode is taking place in a discrete way. Okay, in a discrete way means the charge carriers, when they get released, the charge carrier behave discretely. So that's why the name is given as a quantum tunneling effect. So the literal meaning of quantum tunneling effect is making use of majority charge carrier to penetrate the offered junction barrier potential by the junction of a particular diode. So this particular effect we call it as a tunneling mechanism. So please remember that there is no any other meaning simply to the tunneling effect. The tunneling effect is nothing but the penetration of the junction barrier potential by means of using majority charge carrier released by the device. Okay, and this particular process we call it as a tunneling mechanism. Later we will see that this particular effect of digging the barrier potential of the diode junction is going to offer us this negative resistance behavior. Okay, so with the help of energy band diagram we will see the operation of this particular tunnel diode. Now, a transit time concept is nothing but the finite time taken by the charge carrier to cover the distance or the barrier width of the junction. So, the transit time effect is nothing but the time taken by the charge carrier in order to travel certain distance inside a given material. So, first of all, what are the different uses of the tunnel diode? Tunnel diodes are used as micro amplifiers. We will see that application towards the end. Microwave oscillations can also be generated using this tunnel diode, and the tunnel diodes being a very fast in operation, they are also used as a binary memory element in the construction of computing devices, right? And the characteristics of the tunnel diodes are low in cost and light in weight. They do possess a very high speed of operation. they will consume a very less power. They are going to provide us a less noisy operation when it is compared with ordinary PN junction diode. High peak current to valley ratio is obtained in order to achieve satisfactorily the negative resistance behavior. Okay, now let us go to the theory and understand how the negative resistance of this particular diode is achieved. Okay, so I already explained you what is the terminology of a negative resistance. Okay, so in this particular tunnel diode or Isaki diode, we have a junction, and the junction is formed by joining p-type semiconductor with n-type semiconductor. Now here in the case of tunnel diode, the doping which we use in the construction is very typically high. Okay, so the impurity concentration in the construction of a tunnel diode ranges from 10 raised to 19 to 10 raised to 20 atoms per cubic centimeter. So such a high level of doping is used in the construction of a tunnel diode. Okay, so because of a very high impurity doping, the junction barrier width, whatever it forms when we join the p-type semiconductor with n-type, the depletion region because of this barrier width is going to become a very thin, or the order of around nanometer, 10 raised to minus 6 centimeter, or approximately it is 10 raised to minus 8 to 10 raised to minus 9 meters. So approximately you can consider that the barrier width of such a diodes are in the order of nanometers, right? So when the charged particles, they get excited when we forward bias the diode, the charged particles will acquire the energy with the applied bias, and the energy acquired by the charge carrier is such that it is sufficient for them to easily cross this barrier potential, right? So as per the quantum theory, if the barrier width or the junction width is kept around 3 into 10 raised to 6 centimeter or less than that, then the charged particle, upon applying the bias voltage, they can tunnel through or they can penetrate through a barrier even if they don't possess sufficient energy. So this is a very important effect. So even if the majority charge carrier inside the tunnel diode construction, they are not going to get enough energy, they can still cross the barrier potential, provided if the barrier potential width is around 3 into 10 raised to minus 6 centimeter or less than that. Okay, so the below diagram shows the symbolic representation actual tunnel diode, and on the right hand side the typical construction of the tunnel diode is shown. So symbolically the tunnel diode is represented by a bar like structure which is treated as a cathode terminal, right? So this is a typical symbol over here. Symbolically, the tunnel diodes are represented by a bent bar in front of a diode symbol, and this is a typical package of diode. You can say how it look like, package of tunnel diode. Okay, and on the right hand side a typical construction of the tunnel diode is shown, right? So the p types and n type semiconductor, they are going to form a junction over this particular region. So this is a junction area. Okay, so this junction is formed between p type and n type semiconductor, and typically what type of material we will use, the typical material that we are going to use is germanium and gallium arsenide for the construction, right? And germanium and gallium arsenide, they are going to possess this negative resistance effect, so that we will see in a soon time. Okay, so this junction is formed by p type and n type semiconductor, and these semiconductors are heavily doped, so that whatever depletion region it will possess, that will be a very less. Now let us discuss what is the tunneling effect and negative resistance behavior. Okay, so this particular diagram I will elaborate you over here. Okay, so let us understand this particular diagram. Now here the green color line whatever I have shown, that indicates a conduction band, and the energy of the conduction band is denoted by EC. Okay, and the pink color line over here that indicates the valency band. Okay, so as on when the bias is not applied, so the construction of energy band diagram for the given tunnel diode look like this. Okay, so for understanding purpose, let me draw it again. So let us say the energy band diagram I will draw. I will write it first. Energy band diagram for tunnel diode operation. I will write for tunnel diode operation. So in order to understand the operation of a tunnel diode, we will explain the operation of tunnel diode by means of its energy band diagram, right? So let us say the conduction band is shown in this way. This is a conduction band. Okay, and I will also show the valency band. Okay, so this is valency band. Okay, so this valency band is normally p type, and the conduction band, the majority charge carrier, we will show with n type. Okay, so this is how the p-n junction is formed, and the energy band diagram is shown between conduction band and valency band. In the conduction band, we have majority charge carriers as the electrons. So rather what I will do is I will show this in this way, a little bit lower. Okay, so this is a p type and this is a conduction band, sorry, the valency band, right? Valency band. So the green color line shows the valency band and the red color line indicates the conduction band. Okay, so the p-n junction is formed and the energy band diagram can be illustrated in this particular way when the diode is without any applied bias. So in the conduction band we have the majority charge carriers, so those are the electrons. Okay, so we have electrons in the conduction band, right? And during without any bias, the valency band do not possess any particular electrons. Okay, so this is when the diode is without any particular bias. So this diode, I will show the diagram over here, the biasing of the diode. The diode is like this. Okay, the symbolic representation of tunnel diode, and this tunnel diode is applied with DC bias voltage. It is forward biased. Okay, so this voltage is a DC bias and it is forward biased. Okay, so when there is a no bias condition, so this particular energy band diagram is valid whenever there is a no bias or zero bias. Okay, so if I plot the VI characteristics of diode, right, so without any particular bias there will not be any particular current. So this is a voltage and correspondingly we will get a current over here. So without any applied DC bias there will not be any flow of current through the device. Okay, now what we'll do is we will apply the DC voltage. Okay, now when we apply a DC voltage, the current will start increasing with the applied voltage in this way. Okay, so what happens to the energy band diagram? The energy band diagram, the changes that will take place, that the valency band slowly start coming on the upper side in this way. I will draw with a dotted. Okay, So the valency band, whatever the dotted green line I shown over here, that will get shifted. And already the valency band have lack of electrons, or that is going to possess the holes. Now what will happen is these holes from these electrons from the conduction band, they will find a path to travel into the valency band, and the movement of the electrons from the conduction band to valency band in situation number 1, I will denote over here. This is the situation number 1, during which the applied voltage is just applied across the diode, right? So that the valency band will get shifted upwards, and because of which the electrons in the conduction band, they will see a path to travel to the valency band, and the electrons will start traveling in the valency band, and because of these motion of the electron, we will get a current in the circuit. Okay, so this path I will show with number 1. So what will happen? A current will start flowing. Okay, so when I applied the bias, when I increase the bias, the electrons will start moving from the conduction band to the valency band, okay, rapidly. Okay, so this will happen to a certain point. Okay, so at position number 2 that I will show, what will happen if I still increase the applied voltage, the conduction band rises up to the next level. So let us say this is a position number 2. So the valency band rises upwards. So more number of electrons are going to pass from the conduction band to valency band, and we will get a maximum current, right? So if we still increase the applied voltage further, at one particular point we will get peak voltage, peak applied voltage, at which we will get a peak current. So this peak current is denoted by IP. Okay, so this will happen at a particular point, point number 2, where the valency band is shifted upwards, so that maximum transfer of electron from the conduction band will take place in the valency band. Okay, now if I still increase the voltage such that the voltage is greater than the threshold voltage Vp, okay, so at that time what will happen? The valency band will again get shifted upwards in this way. Okay, and now as it gets shifted upwards, this diagram can be represented as like this. This is the, or sorry, this I will draw it as a, first as a band I will draw, and then I will draw, let us say this is our, okay, and the valency band at position number 3 I will show in this way. Okay, so what happens at position number 3? The valency band shift upward and upward. Okay, so here the same diagram is depicted over here. Okay, so this valency band gets shifted upward and upward, and at one position when we apply the DC bias voltage greater than the peak voltage, at that time this valency band will get shifted upwards, and the overlapping of the valency band with the conduction band will reduce. And what will happen? The electrons which were moving with a fast velocity, now they will start moving with a slower velocity in this way. Okay, so at that time what will happen? The current in the external circuit decreases. Okay, so the current in the external circuit decreases in this way. Okay, and please remember, we are increasing the voltage but still the current is getting decreased. So this is the position number 3, where in the external circuit we are getting the current to be reduced with increase in voltage. Okay, and at point number 4 again, the overlapping of valency band and conduction band will be over almost, and the device will again start increasing the current in the linear fashion, the way in which we get the behavior of PN junction diode current. Okay, so we are interested in a particular region, we call it as a valley voltage, that is a minimum voltage, that maximum voltage we get at that time we'll get a valley current, and this valley current is a minimum. Okay, and a region that we are interested in is this particular region, which I show with this shading of yellow color, where the resistance is negative. Why it is negative? Because with increase in voltage from the peak voltage, when we increase the voltage which is greater than the peak voltage, the instead of increase in the current will start decreasing and the current will fall below, and the resistance at this particular value of the applied voltage I am going to get a negative. Okay, and when I maintain the voltage such that the applied voltage V is greater than peak voltage and it is less than valley voltage, if this particular condition I maintain as an applied bias voltage to the tunnel diode, I will ensure that this diode will operate in this particular region. Okay, so this region of the operation, where with increase in applied voltage the current starts decreasing, this will give me a negative resistance behavior. Okay, and once the device enters operating into this particular region, it can be used to amplify the micro signal, as well as we can modify the circuit and make use of that device as an source of the micro signal itself. So this negative resistance behavior with the help of energy band diagram I explained to you. The same in brief it is explained over here, and the same diagram is shown. Okay, so here we get the peak voltage VP, and here we get the valley voltage VV, and the current corresponding to the valley current is IV, and the current corresponds to peak voltage is a VP. Okay, so in between we whatever the region that we are going to get, so this particular region that I am highlighting with a yellow color, so this region is a negative resistance region, and once our tunnel diode enters into this particular region, it can be used as a source of a microwave frequency, or it can be also used to amplify the microwave signal. Right, so the same is explained with this help of energy band diagram. Okay, so tunneling diodes are going to be used in a forward bias condition. So tunnel diodes, whenever we want to use, they are used in a forward bias condition in order to observe the negative resistance effect which will get developed into them when the applied bias voltage is less than the peak rated diode voltage. Okay, so this particular condition, when the applied bias potential DC voltage V is less than peak rated voltage of the tunnel diode, then the conduction band start getting aligned with the valency band. So this is a very important statement. Okay, so what will happen? The conduction band will start getting aligned with the valency band, and thus the majority charge carrier, which are the electrons in the N type, they will start getting migrated to the P type semiconductor in the valency band. Okay, and thus we will get a forward current in the external circuit because of this movement of the electrons which is taking place from N type conduction band to P type valency band. Okay, which is shown over here. When the forward bias voltage is reaching to the peak voltage value of the specified diode, then the charge transport take place very rapidly. Okay, so when the applied voltage reaches to the peak value of the device, then a rapid transportation of the electrons will take place, which will give rise a very quick and sudden rise in the forward current. Okay, and this can be explained with this particular portion where the current begins to increase very rapidly. Right, so next what we do is we still go on increasing the forward bias voltage. Now when we increase the forward bias voltage such that when it exceeds beyond the peak voltage, when the applied voltage is greater than the peak voltage, then what will happen is the conduction band is going to shift upwards with respect to valency band, and thus the channel transition is going to become narrow. And when the channel becomes narrow, the electrons from the conduction band to valency band transportation will decrease, and thus the current in the external circuit is going to decrease, which gives rise to the negative resistance behavior. So what actually happening over here, we are increasing the applied bias voltage beyond the peak voltage, and what is happening because of this, the conduction band will get shifted upwards, making the channel narrower, and as the channel becomes narrower, the transportation of the electron from n-type conduction band to p-type valency band will decrease. As the transportation of electrons decrease, the current in the external circuit will decrease, right? So the decrease in the current will continue with increase in the applied voltage to the point when it reaches to the valley level. Okay, so this will continue, this effect of negative resistance will continue still with increase in the applied voltage till a value known as a valley voltage. Okay, so if we increase the bias voltage beyond the valley voltage, now what will happen? So this particular region, okay, so when we increase the applied voltage beyond the valley voltage, what will happen? This will give rise to again a flow of a current as per the ordinary PN junction theory. So in this point, after when we exceed the valley voltage, the nominal current will start flowing through the diode, which is same as that of the current that will take place in ordinary PN junction. The negative resistance behavior of the device can be utilized to produce either microwave oscillations or amplification of the microwaves. So the yellow highlighted region in which we need to maintain the applied bias voltage such that it should be greater than the peak voltage, but it should be lesser than the valley voltage. In that particular case, the diode will provide us a negative resistance. And once the diode will start operating into this particular region, this diode can be utilized to produce the microwave oscillations, as well as it can be used to amplify the microwave signals. So the application we will see later on. Okay, so this is what the negative resistance property of the tunnel diode is utilized for, either generation of the microwave signal or amplification of the microwave signal. Okay, so the equivalent diagram of the tunnel diode is somewhat look like this. What we have is the resistance offered by the package and the inductance offered by the package itself. So these values are denoted here with LS and RS. They are representing the resistance and lead inductance offered because of the packaging of the diode, and important part over here is highlighted with red dotted circle. Okay, so here the capacitor and a negative resistance are shown in a parallel combination. Okay, so this capacitance is the capacitance formed because of the junction. Okay, and the equivalent negative resistance is shown in parallel with this capacitor. Okay, so where Rn is the negative resistance which will get exhibited by the diode when we apply a suitable bias. Okay, so the resonant frequency of this particular tunnel diode is given by this particular equation, 1 upon 2 pi Rnc into square root of Rn square C divided by Ls minus 1. Okay, so where we use this particular tunnel diode as an application, the tunnel diode and the tunneling effect can be used as a ultra high speed switching element in the microwave circuits. Okay, so the switching speed is obtained up to picoseconds. So please remember, such a high switching speed can be established by using a tunnel diode. So 1 picosecond is around 10 is equal to 10 to 12 seconds. Please remember. So such a high speed, such a small, okay, so very high speed can be achieved by operating at 10 raised to 12 seconds. So that means this particular diode can switch on and switch off at the rate of 10 raised to minus 12 seconds, and thus it will be a very good application in microwave and a signal which is greater in a frequency compared to microwaves also. Okay, so it is used as a logic memory devices storage. Okay, so it can be used in satellite equipments, and negative resistance feature can also be used in a relaxation oscillator. Okay, so let us see one particular application as an amplifier and oscillator. So here what I will do is I will draw a block diagram where we can make use of this tunnel diode as an amplifier. Okay, so tunnel diode as amplifier. So to use tunnel diode as an amplifier, what we do is we'll make use of a circulator device. Okay, so from the model number 2, passive waveguide based junction devices, we know. So this is the circulator. Let us consider the signal flow in this particular circulator. This is a 3-port circulator, right? I'll draw in this way. So this is the circulator, please remember. This circulator has a characteristic impedance capital Z0. Okay, and this is a port 1, this is a port 2, and this is the port 3. So in port 1, what we do is we will connect our tunnel diode. Now the tunnel diode I will represent with a capacitor and a parallel negative resistance, please remember. Okay, so this is the equivalent circuit of tunnel diode Rn and junction capacitance Cj, right? So this is the tunnel diode which I connected in the port number 2 of the circulator. The tunnel diode is represented by equivalent circuit. Okay, so in port number 1, what I will do is I will connect a signal which I want to amplify. So a small signal which I want to amplify, I will place in a series with generator impedance, and I will connect this at port number 2 in this way. So here the signal which we want to amplify is the Vs, and this signal is applied at port 1 of the circulator with its internal resistance Rs. Okay, supposed to be amplified by this particular tunnel diode. Okay, so this tunnel diode is used as an amplifying device over here, and the amplified signal will be delivered to the load which is connected in port number 3 over here in this way. Okay, so let us call this as a ZL. Okay, so this is a load. Okay, and port number 1 is connected to the source whose signal we want to amplify, and the tunnel diode is itself connected in the port number 2 of the circulator. Okay, so how this will operate as the amplifying device? So we know that in order to make use of this tunnel diode as an amplifier, this should be biased such that it will operate in the negative resistance region. Okay, so once it will start operating in the negative resistance region, right, the characteristic impedance of the circulator must be kept greater than the diode's negative resistance. Okay, so here the characteristic impedance of a circulator, that is Z0, it should be kept greater than the negative resistance of the tunnel diode. So this condition we are going to maintain, and we are going to calculate the reflection. Okay, so when we calculate the reflection that will take place at port number 2, so gamma we can give as negative resistance Rn by Z0. Okay, ZL minus 1 upon ZL plus 1, in that way Rn by Z0 plus 1. We are neglecting the effect of capacitor, so here I will write neglecting parallel capacitor. Right, so this is a reflection coefficient at port number 2. Okay, so we can write this reflection coefficient at port number 2 mod of gamma square the reflection that will take place is greater than 1, or we can say Z0 is greater than negative resistance. Okay, so therefore the power which will get delivered at the load, please remember port 1, port 2 and port 3 all are isolated from each other effectively, right? So the power delivered to the load is then given by power PL is equal to this gamma square, okay, into input power. Now here gamma square is greater than 1, therefore PL is greater than input power. So the output power, this indicate output power is greater than input power, and thus the signal which is connected at the input as an input signal is getting amplified when it's get delivered to the load which is connected at port number 3, and thus we can make use of this tunnel diode in order to amplify the particular signal. Now this will only happen when the negative resistance of the tunnel diode is less than the characteristic impedance of the circulator. Okay, so we can make use of this configuration, and this particular amplifier device by making use of a tunnel diode is sometimes known as reflection amplifier, right? So this is how the tunnel diodes are used as a amplifying devices, right? So similarly the tunnel diodes, when they are employed with a tune circuit or tank circuit, they can be also configured as a source of a micro source, okay, and they can be used as a micro oscillator also. So this is all about the tunnel diode construction, working principle, negative resistance phenomena, the equivalent circuit and application by making use of a tunnel diode, and VI characteristic also we saw. Now we will move ahead to the next type of diode that we are going to discuss is the Varactor diodes. Okay, so Varactor diodes are very simple and they are known as voltage variable capacitors. Okay, so essentially the Varactor diodes are nothing but a voltage variable capacitor. Okay, so what do you mean by voltage variable capacitor? The capacitance of these diodes can be modulated by applying a variable voltage across it. Okay, so the Varactor diode are also sometimes known as a Varacaps. Okay, so Varactor diodes are nothing but they are essentially voltage variable capacitors. Okay, so we can vary the value of a capacitance by applying the voltage and by varying the voltage which is applied across it. Okay, so basically we know how to calculate the capacitance. Okay, so the capacitance is how it is given. Capacitance in terms of a capacitor C is equal to some constant epsilon naught. Okay, it depends on the area of the plate and it inversely depends upon the separation between the plates. Okay, so when the separation of the plates is increased, so when this separation of the plate is increased, the capacitance will decrease and vice versa. Okay, and how we can vary the separation between the plates? The separation between the plates can be varied by applying the voltage across the diode. Now we know that in a diode we have the junction. The junction will act as a plate, parallel plate, and this junction width can be varied by applying the voltage. When we forward bias the diode, the junction width will become lesser and lesser, and as junction width will become lesser, the separation will decrease and the capacitance will increase. On the other hand, if we reverse bias the diode, okay, so the junction width will become large, right? So the separation will increase and the capacitance in that case will decrease. Okay, so in front of you on my right hand side there is a symbolic representation of Varactor diode. Essentially Varactor diode is a voltage variable capacitor, right? So a voltage controlled variable capacitor, we call it as a Varactor diode. and here the PN junction is going to form a barrier potential. Now when we apply a reverse bias across the diode, it will increase the barrier width, right? And the barrier acts as a capacitor. So this sentence is very important. The barrier acts as a capacitor, and hence the capacitance can be varied by using the applied bias. Okay, so if we forward bias, the junction barrier will reduce. When the junction barrier will reduce, the distance of capacitance plate is going to reduce and the capacitor will increase, right? On the other hand, if we increase the reverse bias, the width of the junction will increase, okay, and that will decrease the capacitor. So here we can obtain variation in the capacitance, okay. And one may ask why we want to use this variable capacitor and where we are going to use. Now the answer is we are going to make use of variation in the capacitance in order to vary the reactance, okay. And next question is where we want to utilize this variation in the reactance. The variation in the reactance can be used in a variety of different ways. Variation in the reactance can be used to generate a new signal, to multiply the two signals, okay, and also the variation in the reactance is utilized to achieve the modulation process also, okay. So the variation in the capacitance, so here it is going to generate change in the circuit reactance, okay. So this is what we want. We want to vary the reactance of the circuit, okay. In order to vary the reactance of a circuit, we can vary the capacitance. So how the capacitance is varied? The capacitance is varied by means of varying the voltage across the diode. So when the voltage varies across the diode, the capacitance tends to change, which will be formed by the barrier potential, right? And when the capacitance changes, the reactance offered by the diode is going to change, okay. Now the reverse bias junction will act as a voltage controlled capacitor, okay, and whatever capacitance we are going to get as a variation of the applied voltage is nominally a non-linear function, okay. So please remember, whatever variation in the capacitance we will get with this diode, it will be non-linear function of the applied voltage. And the characteristics of Varactor diode is shown on the right hand side, okay. So when we increase the reverse bias on the left hand side, when we make the potential more and more negative, what will happen? The junction width will become more and more. As the junction width becomes more and more, the capacitance will decrease and we will get such a kind of a curve in this way, okay. So here actually how the Varactor diode look like, this is the construction, this is the details. Over here it is shown in the construction, Varactor diode construction. It is a normal PN semiconductor junction diode, okay, and it is used in a reverse bias especially in order to vary the capacitance, okay. And the working principles are explained over here in this box, operation of the Varactor diode, and the operation is very simple and straightforward to understand. So here in the first diagram over here, this Varactor diode is reverse biased by applying a voltage of 3 volts, okay. So when we apply a voltage across a diode around 3 volt, the junction will get reverse biased and the junction will have certain width offered during that applied reverse bias, let us say W1. So when the width of this junction is W1, the offered capacitance of this particular diode will be in the range of 20 picofarad approximately, right? So what we'll do in the second figure, we'll increase this reverse bias to a double value, okay. So what we do is now we increase this reverse bias voltage to 6 volt, which is double than the earlier case. Now what will happen? Because of increased reverse bias across the diode, the junction width will become increased, and let us say this junction width is W2, and the junction width relationship is the width in the second case of the junction is greater than width in the first case, okay. So what will happen then? The separation, this junction will act as a capacitance distance, okay. So in the second case, the distance is increased between the plates, so the capacitance value will fall below to around 5 picofarad. So earlier it was a 20 picofarad, and when I increase the reverse bias, the junction width will become increased, and which will increase the capacitor plate separation, and when the distance increases, the capacitor falls down from 20 picofarad to 5 picofarad, right? So this is how we can achieve variation in the capacitance. And where to utilize this variation in the capacitance? The variation in the capacitance is going to result in the variation of the reactance, right? So therefore Varactor diodes can be used in a variety of a different application. They are normally popularly used in switching and in modulation operation of the microwave circuits. Okay, they can be also used because they are capable to alter the reactance of the circuit. By altering the reactance of the circuit, they can produce multiple frequencies, and thus they can be used as a harmonic generators. Okay, so the harmonic means multiple frequency of the fundamental, right? So these diodes can also be used for conversion of the frequency in the mixing operation. These diodes can also be used for an amplification, and especially that we are going to see in a detail, Varactor diodes are the basic building blocks of parametric amplifiers. Okay, so a most very popular application which makes use of Varactor diode for their operation is the parametric amplifier, and these parametric amplifiers we'll see in a detail. Okay, so when we come across the Varactor diode theory and parametric application, they are also used in a pulse generation and shaping circuits, right? And they are used in a radio tuner and frequency multiplier also. The equivalent circuit of the Varactor diode is shown over here. Now the equivalent circuit of a Varactor diode consists of a series resistance because of the package, right? And it has a variable junction capacitor. Okay, so which is denoted by Cj. Okay, and it has a variable junction resistance also, which is denoted by Rj. So this variable capacitor and variable resistors are shown in parallel with each other, and both can be varied. Okay, so essentially the Varactor diodes are voltage controlled variable capacitors. Okay, so by applying and by controlling the reverse bias across these diodes, variable value of capacitor we are going to get. This variable value of capacitor can be used to vary the reactance of the circuit, and by varying the reactance of the circuit, we can use these particular diodes in variety of different ways: harmonic generators, frequency multipliers, frequency conversion, pulse generation, parametric amplifiers. All these applications are going to make use of variation in the reactance, and for that they need to rely on Varactor diodes or voltage variable capacitors, right? So this is all about Varactor diodes, the operating principle, the construction, the VI characteristic, right, the applications, and the equivalent circuit of the Varactor diode. Okay, so today we saw two important diodes, tunnel diodes, which are also known as a negative resistance diode, or sometimes the other name with which they are known as a Isaki diodes. Okay, and the second type of a diode we saw, that is the Varactor diode. Okay, so I hope you understood the working principle of a tunnel diode and Varactor diodes and their usages. Okay, and in our next lecture we'll continue with special type of semiconductor diodes which are very popularly used in a variety of microwave different signal processing. Okay, so in our next lecture we are going to see two distinct categories of special type of a microwave diodes. One category is based on the principle of transferred electron mechanism, and the other category of a diode which principally based on the transit time effect of the diodes. Okay, so one diode which is principally dependent on a phenomena called as transfer of electrons, and the second type of a diode category that we will see, those are known as a reed diodes or impart family diodes, which are essentially transit time devices. Okay, and lastly we will see the application of Varactor diodes, especially in a parametric amplifier. Okay, so I hope you understood today's two chapters, tunnel diode and Varactor diodes. And in our next lecture, we will be starting with very important category of diodes, transferred electron devices and transit time diodes. And lastly, we are going to see and explore the operation of parametric amplifier using Varactor diodes. Thank you very much. We'll stop here.